A bunch of people in Loveridge's class have been wondering about question 5 on the test, and I decided I would just show you guys a neat way to go ahead and put these kind of setups in practice and see what they would actually look like. Obviously, this isn't real life, but this is the closest you can get in terms of a simulator. This thing is great. So this is the circuit construction kit. It's a FET simulator. I'm not sure if Loveridge showed it to you guys, but Westling showed it to us last semester, and it was pretty wonderful. So just want to get back into it. Really quick, a couple things before I start. If you notice when I press play here, the current flow seems to go opposite of what you guys would expect. As you see, the charges are flowing through the positive and out of the negative rather than the other direction. And that's because the simulator actually uses the real flow of charges, which is electrons, and they would obviously move to the positive end out of the negative end, rather than the other way, which is what we use with protons. And we do that to make all the math easier, because if not, everything would be negative, yada yada yada. There you go. So let's just jump into it. Part B of number 5 was asking, the setup was that the EMF of 2 was equal to the voltage drop across battery 1. So really quickly, just to show you guys what these numbers mean, this number represents the EMF. This is the internal resistance, so same thing going on here. And this is the actual voltage drop across the battery when there's current flowing through it. So let's go ahead and set up part B, just part B. So E2, the EMF of 2, is equal to the voltage of 1. So let's go ahead and change the voltage here, which is the EMF. I'm going to set it equal to this number, 8.182. Done. The values disappear for a second and bring them back. So as you'll see, the EMF is equal to that. And let me go ahead and close the switch. And you'll notice that there is no current through branch 2. And this is in pretty much everything. The one thing to keep in mind for this entire problem is that all three of these branches are in parallel, and they want to keep each other at the same voltage. All branches want to be at the same voltage here. So if you have the EMF of battery 2 already at 8.18 volts, and I close this switch, there should be no current running through it in order for it to maintain the same voltage across the battery. Because if not, if there was any sort of voltage, it would either go lower than 8.1 volts, lower than 8.182 volts, or higher than 8.182 volts. And so as you can see, as I just demonstrated, there is no current running through it. So what does that mean for the rest of the situation? By the way, that was your answer to part 1, no current. Part 2 was what will happen to the current through battery 1. As you'll see, nothing. The current through battery 1 stays the same. And the third part of this was what will happen to the brightness of the bulb. Obviously, if the current is the same all around, then the brightness of the bulb will stay the same. And that's pretty much it for part B. So part C was the EMF of 1, battery 1, is greater than the EMF of 2, but the voltage of battery 1 is less than the EMF of 2. So in order to set that up, we'll need the EMF of battery 2 to be less than the EMF, less than 9 volts, but also greater than 8.18. Actually, let me go ahead and open the switch first. So I'm going to go ahead and change the EMF now. Let's make that 8.5. It's okay, we don't need to... These numbers, by the way, I know he didn't specify the internal resistances or the EMFs, but as long as our numbers fit into the situation he would like us to have there, it's fine. So let's show the values again. Now let's go ahead and bring the ammeter back here, 0 amps, because the switch is open. I close it, and now we have current flow. And as you'll see, the current is actually flowing in the direction that this battery would want. I know it looks like it's flowing down, but for you guys, you would say that it's flowing upward because of protons moving rather than electrons. So this current for your answer is moving up. There is a current through battery 2. As I said before, the key to this is that each one of these branches wants to be at the same voltage as the next branch. So if the EMF for battery 2 was at 8.5 and the voltage drop across battery 1 was at 8.182, in order for these branches to meet to a level term, the voltage drop across battery 2 would have to be lower than 8.5, which it is now, 8.33, as you can see if I bring this over here, and it is now equal to the voltage drop across battery 1. So the voltage across battery 1 increases, the voltage across battery 2 decreases, or what I mean by that is it's not equal to its EMF, it's lower than its EMF. So I can't really say the voltage decreases, that's not exactly right, but it's lower than its EMF. And there's a good middle ground there. And as you'll notice, the EMF across the battery, or the voltage, sorry, I keep mixing those two up. The voltage drop across the battery is pretty much the same as the others as well. So what does that mean for the current of battery 1, which is part 2? Part 1, by the way, we said that battery 2 will have current through it, and it will be moving upwards. So now what happens to the current through battery 1? Will it increase, decrease, or stay the same? I close the switch. As you'll notice, it decreases. And in order for the voltage to increase, this current would have to decrease. As you know that the voltage drop is equal to the EMF minus the IR, the internal resistance, times the current through battery. So in order for that second term to become less, the current would have to decrease in the battery, and so you get a higher voltage coming out of this battery. So what does that mean for the brightness of the bulb? Well, let's go ahead and bring the current, the ammeter, to the bulb, and as you'll notice, it increases as well. As you would expect, if the voltage across the branch increases, the current increases. So you'll see as I open the switch, it's 8.18. When I close it, it's 8.332. So the brightness of the bulb increases. This is C part 3. So that's it for part C. Now part D is asking us to set up a situation where the EMF of battery 2 is less than the voltage of 1. So once again, the voltage of battery 1 is 8.182. So let's make the EMF of battery 2 less than 8.182. So I'll just make it a solid 8. And let's see what happens when I open the switch. Let's bring the ammeter over to battery 2 actually. So I'm going to close the switch, and you'll notice there is current. However, this time it's moving in the direction opposite of the way this battery would naturally push current, meaning that the negative charges here are going through the negative terminal of the battery. For you guys, that would mean that the current was going down in this case. So for you, part D, number 1, the direction is down. And the logic here is the same as it was for the last. This time, let me bring up the values. The EMF of battery 2 is starting at lower value than the voltage drop across battery 1. And since all these branches want to be at the same voltage, this voltage would have to increase in order to meet this voltage somewhere in the middle. So as you'll see, when I close the switch, the voltage drops across battery 1, and that voltage that it drops to is equal to the voltage across battery 2. And battery 2 got there by having a current that is negative to its natural flow, which increases the voltage to a higher value than its internal EMF. And as you'll see, what does that mean for the current across battery 1? Let me go ahead and open the switch. Sorry, I keep mixing those up. As you'll see, when I have the switch open, it's 0.82 amps. When I close it, it is 0.9. So like I said before, that the EMF minus IR, in order for that to decrease, the resistance isn't changing, so the current would have to increase. So what does that mean for the bulb here? Well, if the voltage is dropping across across the branches, you would expect the bulb to be dimmer, right? And that is what's happening. You'll see here when I bring the ammeter I'll go ahead and open the switch again. You'll see when I close the switch, the amperage, the current, decreases. And like I said, the voltage decreases, you would expect the current to decrease. And that's it for part D. Um, Let me know if you guys have any questions. I hope that explanation was sufficient. Um, and like I said, this tool is very useful, so I would highly recommend using this in the future. Thank you. That's it.